Hello, my name is Cliff Goldstein. I'm with Eclipse Engineering. We're a manufacturer of seals and different types of polymer profiles. Today we're going to have a discussion on rubber energized seals, but we're going to start with some basics. We're going to basically cover how seals perform, what it takes to do seals, and we're going to end up with rubber energized elements like urethane or PTFE or Teflon. A little background: Eclipse Engineering, we design and manufacture high performance polymers. We make a variety of different types of seals, specifically rubber energized seals, spring energized seals, and rotary seals. And today our focus, as we've stated, is going to be around how rubber energized seals work. So the first thing that we want to discuss is some seal considerations. And whenever we go into the design process, we ask ourselves, what are the criteria that are going to decide what a seal is going to look like? So I start off with cost being number one, because if we're into the automotive industry, typically these seals are low cost, and we've got to find a way to keep our dollars down. We look at things like the pressure, the system pressure, the types of fluids that are involved, the exterior environment. In other words, we're going to be operating in very cold temperatures or very hot temperatures. So temperature has a great big impact, or a large impact. Friction is another area. Is friction important in the application? And to what level is friction important? Finally, again, I mentioned briefly before, but fluids are important. Are we going to be sealing a gas or a liquid? And will that fluid remain at one viscosity, or will it be changing viscosities? And finally, if you'll notice on the slide, there's two signs there that say cost. And oftentimes, we'll start off a lot of our discussions with engineers, and cost is no factor, but we know that cost always enters into the formula. I always like to start off with what the perfect weld joint is, and if we could weld all of our joints together, we'd have perfect seals. But in reality, even a welded joint has a certain level of porosity. And so we need to make a determination as to what we consider an acceptable level of leakage, because no seal will have a zero level of leakage. Even that welded joint will have a level of porosity. So we look at these different weldments. I showed you a butt weld to begin with, and now I'm showing you two faces coming together. And we're going to move from here in just a second. But these weld joints are typically tested with helium leak down tests. And in a lot of applications where we're sealing a gas, helium is often used as a method of determining what the level of leakage, level of acceptable leakage is, because we know that there are no perfect seal joints. Going forward, a very common type of seal is a gasket, and these gasket materials can range in a variety of different materials. Some of the original gaskets were, of course, cork. There's paper gaskets. There's complex gaskets that are made out of metal, so we have metal C-rings, or even soft metallic elements can be like a brass or a bronze can be used as a crush gasket in certain environments. So gaskets take on a lot of different forms, but one of the simplest gaskets is, of course, that does a good job, is an O-ring. And the nice part about an O-ring is that it has some resilience. So when you install an O-ring into one of these face seal joints, there is a level of tolerance so that when the two faces come together, we can, with the proper amount of clearance, knowing what kind of pressure we have, an O-ring does an excellent job of sealing. And for all practical purposes, excluding things like gaskets, like what you have on a valve cover or on a head gasket, O-ring is a pretty common static type of seal. And depending on the pressure, it might be an O-ring. It might be an O-ring with a backup ring. And what I'm showing now is an O-ring with a backup ring. And if we go back to the previous slide, if our pressures typically are under about 1,500 psi, an O-ring without a backup ring is a very common way of sealing a static joint. Similarly, when our pressures exceed 1,500 psi or our extrusion gaps begin to get rather large, we'll use a backup ring to help to retain the O-ring. Now, the purpose of that backup ring is so that when the system is pressurized or energized with a fluid, the O-ring will drive into the backup ring and force the backup ring into the extrusion gap. Without an extrusion gap, without a backup ring, typically an O-ring will nibble or deteriorate in that joint. You can't really go forward too much further in rubber energized seals without having a little bit of an understanding of what these O-rings look like. This is a page out of the Parker O-ring book. This is a pretty standard page, and what it has in it is the standard cross sections for O-rings, and there's 5 standard cross sections going from 0 series to 400 series, and in this table it actually shows what the glands would look like. And so when we're doing design work with just O-rings, or even designs with O-ring energized Teflon seals, we'll use these types of interferences and make sure that we have enough gland clearance so that we don't distort or cause the O-ring to have a premature failure. An O-ring energized Teflon element relies on both elements to continue to perform. And so even though the O-ring is static, it's moving around in the joint. If we don't give it enough room due to temperature or pressure considerations, we can prematurely fail the O-ring, which will fail the O-ring energized Teflon seals prematurely. You'll notice that there's a couple of important lines in here. One is the L gland depth, and that tells us in static seals what those glands ought to look like for gland depth. And of course groove width, and that's to make sure that the seal has enough clearance inside the groove. Now this particular chart also has a 1 backup ring and a 2 backup ring groove width, and we use those when with multiple backup rings to make sure or to ensure that we do have the proper clearance for the O-ring in the groove. And just as an initial discussion, one of the items that we talked about early on was friction. And this is another page out of the Parker O-ring book, and it gives the force per inch of the different O-rings under different levels of squeeze and different durometers of O-rings. So lower durometer O-rings produce less force, higher durometers, correspondingly give higher force, and depending on how much squeeze we put on the O-ring will determine how much load per inch that an elastomer will provide in sealing, both as a dynamic seal or as a static seal under a Teflon element. So when we're calculating friction underneath the Teflon seal, or calculating friction with a Teflon seal, we use these charts to tell us that under 0 pressure, how much load is being generated just from the elastomer. The other component when calculating friction will be the actual fluid operating on the seal cross section. So we use both those components when determining how much friction the seal is generating. that and the combination of the coefficient of friction of the raw material determines how much drag will be on that system, whether it's rotary or whether it's reciprocating. If you have questions, please feel free to contact your local distributor, or of course you can contact Eclipse Engineering. And thank you very much for listening.